Okay, some more trig limits here for you. So we're going to start off with these two formulas. I will not prove this one, but later on I'll talk about how I can use part A to prove part B. But for now, we'll just take these two formulas as given. So pause and copy if you haven't done so already. And we're going to make use of these two formulas to find some other limits. Okay, so the first one is the more useful one. So sine x over x goes to 1. You could write that as sine x over x goes to 1. It's kind of a short form. So we'll use that over and over and over again. Okay. First example is not quite the same as sine x over x. So sine x over x will go to 1. This is going to go to something a bit different because the 7x is not the same as 3x, and it is going to matter. You'll notice in this formula here, I have the exact same thing here, and that is important. But I can still use this formula to say something here. So what I need to do is I need to say, oh, I want to use this. So I'm going to force the number here to be the same as the number here. Well, I can't just do that. You can't just use wishful thinking and get what you want. You have to multiply by something so that this equal sign makes sense. So how can I multiply this by a number to get my original fraction up here? Well, what do I need to do? Well, I need this 7 to turn into a 3. How can I do that? Well, I can make the 7 go away by putting it on top of a fraction over here, and then I can divide by 3. So you can check now that this fraction equals this expression here. If you cancel the 7's, you got sine 7x over 3x. Okay, the whole point of this song and dance is to put myself in a situation where I can use the formula over here. Okay, now I have 7x here, and I got the same thing here. So the limit of this fraction will indeed be 1. So we'll get 1 there. And the limit of 7/3 is just 7/3. So I get 7 over 3. Okay, so the principle is that I want to use this formula. And I have to manipulate my expression to make this show up. Or if you prefer, you can write it as sine theta over theta goes to 1. As theta goes to 0, of course. Okay, let's try another one. This one's a bit trickier, but it's the same principle. I want to use this formula. Sine theta over theta goes to 1. So I want to make this appear in this fraction here. So I do some manipulations here. So I'm going to go and take this fraction, kind of factor it. Then I will recall that tan of an angle is sine of the angle over cosine of the angle. So I get sine x over 1 times 1 over sine 2x over cos 2x. Okay, getting a little hairy here, but I promise this is going somewhere. Let's keep rolling. Sine x over 1. Now I have 1 divided by a fraction, so I just flip that fraction. And now again, I'm going to try to use sine theta over theta goes to 1. So let's force that to show up. So I've got sine x over, let's say something. Then I've got 1 over sine 2x times cos 2x over, let's just leave these blank here. So I'm going to fill in these blanks here in a way that allows me to make use of this formula here and also makes this equal sign true. Let's go in blue here. So what do I want? Well, here I want to have sine x over x, right? And here I want to have sine 2x over 2x, because again, I want it to be the same number here as I have here. Now, what do I need to put here to make this equal sign make sense? Well, I inserted kind of artificially the x and the 2x. The x's here cancel, so I don't have to worry about them. The only thing I need to worry about is this 2 here. But if I put that 2 down here, then I'll be in good shape. Okay, you can check now that all the stuff in blue cancels. So this equal sign is indeed true. Okay, now I can use my limit here. Now if sine theta goes to theta, I suppose it's not completely obvious, but the reciprocal will also go to 1. So this guy here is going to go to 1. This guy here is also going to go to 1, so times 1. Cosine, well, I'm doing cosine of 0, right? Because x is going to 0. Cosine of 0 is 1, and then divide by 2. And I get, as my final answer, 1 over 2.